share your screen.
Exactly. I stopped to share my screen. No, okay, okay, okay.
Yeah.
Perfect. Thank you.
Thanks, Nassim.
Okay. Let me share my screen. Yeah, there we go. So, okay, I will tell you about a recent paper that I have sent a few months ago, which discusses the interaction of the supernova, GRB, and the cocoon. And I will try to convince you that this interaction actually leads to a very large landscape, which has not been explored in detail yet. This work has been done in collaboration with Pawan and Peter. And let me start just mentioning something that Nissim has already mentioned. This is our usual current picture of a gamma ray burst. So we have a central engine producing, oh, let me put my, yeah. This is the central engine, a central engine producing a relativistic jet. And the relativistic jet, the dissipation of the kinetic energy into thermal energy leads to the emission of the gamma rays and the multi-wavelength emission. And it's becoming increasingly clear now that in addition to this relativistic collimated jet, we have also other components. So this is a simulation of an example of a simulation of a jet. So the jet propagates into the ambient medium. The interaction, the shocked material expands laterally, forming this extended cocoon. This has been considered by a lot of papers in the last 10 years or so. And this cocoon actually emits radiation, which can be detected mainly if we observe this object of axis, as in the case of the GRB 1708, 17A. And let me go back to these simulations, and I will show you now numerical simulations of the long gamma ray bursts. So you see here a progenitor star, which has a radius of order of the radius of the sun. And I will show you numerical simulation launching the jet from the edge of the iron core. So this is something around 2×10⁸ centimeters. Everything here is rescaled to the speed of light, but as a reference, so this corresponds to 2×10⁸ centimeters. And the jet is just launched from the edge of the boundary. We do not follow the formation of the jet from the central engine because that would require GR, MHD, general relativity, MHD, neutrino transport, and so on. So much more complex physics. Okay, and you will see in the simulation the propagation of the jet to the star. The jet will break out of the star and will expand in the ambient medium. So the jet expands through the star. After a few seconds, it breaks out from the star. This large cocoon expands laterally. It shocks with the other component of the cocoon coming from the other way. And yeah, here the box is expanding at the speed of light. So you see that the relativistic jet on axis propagates at relativistic speeds. And here you can see actually this, after 20 seconds, the jet is stopped. So you can see actually that this is the jet, this shell here. And the cocoon expands laterally also at the beginning at relativistic speeds before decelerating and moving at mildly relativistic speeds. Okay, you can see here the deceleration of the cocoon at a later stage. This is the final outcome of the simulation. So you see the jet here, which is really not a jet, is a shell. Okay, here inside this very tiny shell with the size of order of C times the duration of the jet, the T90, CT90, let's say. We have internal shocks, which interaction leads to dissipation of energy and to the gamma ray emission, or the photospheric emission could be another option for the gamma ray emission. And the cocoon, yeah, it's accelerating, moving with mild relativistic velocities. Depending on how we see the jet, if we see the jet on axis or off axis, we can see the jet only, or we can see at the beginning the cocoon component, and after a while, when the jet is accelerating, we can see the jet. This is what has been seen in the 1708-17. Yeah, in that case, it was a short gamma ray burst, so the simulation really doesn't apply to that case, but it's completely similar now. It's analogous, the problem. There is something missing in this picture, the supernova. So you know that long gamma ray bursts are associated to supernovae, but supernovae are not usually included in the simulations, okay? The question that I will make in particular is which came first, the jet of the supernova? Because as I will argue, this is something very important to determine the outcome of the system, okay? We have different mechanisms to produce the supernova. We don't know really which one is the correct one. We can produce the supernova by neutrinos. This is the usual mechanism supposed to work in regular supernovae. We can produce, in the context of collapsars and gamma ray bursts, we can produce the supernova by energy deposition by magnetar. And there are a few papers discussing this. So the magnetic field collimates the jet, and there is this expansion of this extended structure, which energy deposition can lead to a supernova. The other option is a disk wind. So the disk, which is produced during the collapse of the iron core, which leads to the formation of the jet, can also have a disk wind, which can also power the supernova. The point is, which one can come first, the supernova or the jet? And the answer is that, well, we don't know, because there are many models, many possible models, and we can imagine two different situations in which the jet can come a little bit before the supernova or the opposite way. So, for instance, imagine that the jet starts propagating in the collapsing iron core and can be drawn by the collapsing material until when the run pressure from the jet becomes larger than the run pressure from the collapsing material, while the supernova has exploded a few seconds before. So the jet can be launched a few seconds after the supernova. Or the other way around, the jet can come first and the disk wind can be suppressed at the beginning and can come only after a few seconds. So we can play a little bit with that. Observationally, there are not really strong constraints. There is a paper by Campana showing that there is a constraint of tens of thousands of seconds between the two components. I will show you now numerical simulations of similar to those that I have shown you before, but including also the supernova. So all the numerical simulations show the number density in this Scholar scale. And here, in addition to launch the jet from this boundary, I will launch also spherical supernova. So you will see first the supernova coming out, and after 2 seconds, I will launch the jet. Sorry. After 2 seconds, I will launch the jet. So there we go, the spherical explosion. This is the supernova shock front. And after 2 seconds, we have the jet. And now I want you to focus on the supernova. Let me go back again. So the supernova arrives first to the edge of the star. There we go. Here there is the edge of the star. The supernova breaks out from the star. It accelerates into the interstellar medium, in the circumstellar medium. And the jet remains trapped inside the supernova. Okay? The jet can break out from the supernova at a later stage or not. That depends on the particular, on the value of the energy of the jet, the delay between the launching of the jet and the supernova, and so on. So there are very different factors which will play a role in that situation. Now I will show a different simulation in which I have also the supernova launched before the jet, but the supernova has a little bit lower energy. So here again, we go with the supernova, we launch the jet, and the jet now breaks from the supernova when the two are still inside the star. The jet arrives first to the edge of the star, breaks out, there is this cocoon, and the supernova arrives to the edge of the star, and it expands in a very aspherical way. So the shock breakout from the supernova here is very aspherical, which is something interesting that was not shown before, because this can have consequences on the characteristic emission from the shock breakout. Okay. So in synthesis, this is the picture that I am showing you. Here in this schematic representation, you can see in gray the progenitor star, in yellow the supernova, dark blue is the jet, light blue is the cocoon. Okay, so case A, in this case, the supernova arrives first to the edge of the star. This is the first simulation I have shown you. The supernova arrives first, the supernova accelerates at the edge of the star, and the jet, well, the jet can just be drawn inside the supernova, energizing the supernova. Maybe this could be a mechanism to produce a broad line regular supernova, or the jet can break out at a later stage. This can happen only if the jet is very close to the shock front of the supernova, when the shock front of the supernova breaks out from the star. If not, the jet will just be drowned inside the supernova. The other possibility is that the jet breaks out first from the star because it is launched before the supernova, or because it is launched more or less at the same time, but the energy per solid angle in the jet is larger than the energy per solid angle in the supernova. The jet can break out first, and here there are two subcases. When the jet breaks out, as I showed you before, there is this cocoon expanding laterally. If the cocoon arrives to the equatorial plane before the supernova breaking out from the progenitor star, then when the supernova breaks out, it will break out in the cocoon, okay? And the supernova will propagate into the cocoon. The other case is that the cocoon will expand laterally, but before arrives to the edge of the star, that will take tens of seconds, let's say, from when the jet is launched. Before the cocoon arrives to the equatorial plane, the supernova breaks out from the progenitor star. In that case, we will have the supernova. If we look to this system from the equatorial plane, we will see the supernova here and the cocoon at smaller polar angles. So we can have these configurations in which an observer located at a different position can see the supernova with inside the jet, the cocoon with inside the supernova, or the cocoon and the supernova, depending on the polar angles, okay? And this, of course, has important observational consequences, no? As you can imagine. So let me just mention very briefly that the paper that we have done is more like a qualitative discussion of this. So the non-thermal emission, we have three components: the jet, you can see here the flux as a function of time, so light curves. In radio, for a regular luminous GRB located at the redshift of 1, seen at different angles. So here you have a GRB emission, here you have an off-axis emission, and here you have a more off-axis, completely off-axis emission seen from an observer located on the equatorial plane. So the GRB is very dependent on the observing angle because, well, we know the GRB is collimated, so it depends strongly on the observing angle. The supernova, here I'm assuming that the supernova is spherically symmetric, so there is no dependence on the observing angle. The cocoon has a weak dependence on the observing angle because the cocoon is, it's elongated, but it's more or less spherical, okay? So at the beginning, the GRB dominates. If it's seen on axis, if it's seen off axis, already the cocoon can be important at early times, okay? At late times, it seems that the cocoon can dominate the emission. And this is actually something that was observed by Frey in a paper discussed in a lot of GRBs, this flattening of the GRB light curves seen in a few GRBs observed at the late times. This was interpreted as the transition to the non-relativistic regime. Another explanation is also the fact that the cocoon is beginning to dominate at the late stages. If instead of considering a GRBs, regular luminous GRBs, we take low luminous GRBs, so we drop the luminosity of the GRB and the cocoon, because if we drop the luminosity of the GRB, also the cocoon energy deposited is smaller. We can have this double-peaked structure in which at the beginning we see the cocoon and after a while we see the supernova. And this was actually observed in a GRB. The paper is not published yet, but yeah, there is a case in which it was indeed observed, this double-peaked structure, okay? And yeah, depending on the angle, no? We can have, the GRB can be more important at the beginning or not, depending on its luminosity, and the supernova can be more or less important sorry, the supernova is the beginning, no? After 10 days or so, and the cocoon can be more or less important at the later stage. Okay, so we can have different combinations of these three components depending on the particular configuration in which we are. Okay, as we will begin to see more and more GRBs of axis, we hope at least, which one of these configuration is physically possible and its consequences on the central engine will be clarified. Yeah, and also the other important point is that if the luminosity of the GRB is very small, we will just see the emission from the cocoon, and this was actually seen, at least we believe so, in the supernova 2009 BB. This was a relativistic supernova that we interpreted as the emission from the cocoon, and here in the points are the radio light curves and the dark and the gray and the pink regions are the models, so the emission from the cocoon, trying to explain the observations by directly the emission from the cocoon. Okay.
1 minute, please.
Sorry, how much?
1 minute.
1 minute. Okay, so I will just mention very quickly that there are different possible components for the thermal emission. So first one is the cocoon. The cocoon emits X-rays emission. This is the spectrum in X-rays. And yeah, it's nearly a black body. The red one is a black body, and this is nearly a black body. I will jump this just to show that this was indeed observed in a paper in Nature by Luca Izzo, the supernova 2017 UC. This was the observation by Luca, and these are actually the model coming directly from the numerical simulation. So there is this peak in X-rays going down in frequency as a function of time. And I will very quickly jump the rest, just to mention that the most interesting part, or a very interesting part, is the case in which the supernova is inside the cocoon. The optical emission from the supernova will be partially reprocessed by the presence of the cocoon. The shock front of the supernova will interact with the denser cocoon material, so it will probably emit UV and X-rays, and so on. And this needs to be computed by a radiation transfer code to be explored in full detail, okay? And to see if this is it's possible to explain the different objects seen as more or less broadline type 1c supernovae and other objects also by this landscape of cases. So let me go to the conclusion. The normal GRB top hat with only the relativistic component is a good approximation of a gamma ray burst if we see it on axis. If we see it off axis, we need to include the different components. So we have the jet, we have the cocoon, which is the material expanding laterally. We have the supernova in the long gamma ray burst case, or the kilonova in the short gamma ray burst case. It's not identical in that case, but it's qualitatively similar, the discussion. And depending on the time scales, energies, opening angle of the jet, and so on, we have different configurations which can lead to very different observational outcomes. Thank you very much. 16 minutes.
Thanks, Fabio. So, Diego have one question.
Yeah, hi, Fabio. So I didn't quite follow. So in your simulations, what was the variable which made for the jet to be before or after the supernova?
Yeah, okay. In principle, the main variable will be the delay between the two of them. But in the simulation, I was just changing the energy of the supernova. So if you put a larger or a smaller supernova energy with the same delay in time between the supernova and the jet, so to be concrete. So in my case, the jet was injected 2 seconds after the supernova, and the supernova had an energy of 4 times 10 to 52 in the first case, and 10 to 52 in the second case.
Yeah, because you have tons of variables, no? You have the energy, you have the collimation of the jet, you have the energy of the jet, you have the delay. So there's
in the paper we discussed that this is just for illustration purposes, no? Because really, I mean, if you can start the jet with you can start the supernova with 4 10 to 52, but if the jet is launched 1 second after the supernova instead of 2 seconds, the jet will probably break out from the supernova before it reaches the surface of the star. No, okay. If you launch it with the same energy but a smaller opening angle, the same. No?
And just so what do you think is before, like the egg or the chicken? What is before, the jet or the supernova, or the supernova or the jet?
Yeah, we don't know, no? The interesting part.
Yeah, but what is your feeling? Like, what did you?
My feeling is that there is a variety of possibilities. In some cases, you get a successful GRB. In some cases, you have a type 1c supernova, broadline type 1c supernova, depending on which one. Maybe different mechanisms are at work. No, maybe when you have a magnetar, you get first the supernova breaks out. When you have when you have a neutron star magnetar, you have first the supernova, and after that the jet, which is energizing from inside the supernova. And in the opposite case, when you have a collapsar, so a black hole, you have a successful jet and the supernova inside. So that's my feeling.
Okay, thank you.
You're welcome.
Okay, now Stefan.
Yes, it's more a question because your talk is very interesting, Fabio, and clearly there is a lot of consequences for us. But I have a small suggestion, and it's also for Rosa. Please, when you send your slides, can you also send the reference to your papers, the link to your papers, which are, it's not only for you, Fabio, it's
okay.
for speakers. Because for me, typically, when I've seen your light curve, I need time to understand.
Yeah.
So I think it can be very useful if you send the key links for your talk, associated to your talk.
Yeah. Thanks.
It will help. Rosa, you have understood?
The idea here was just to give a general picture, because I know that it's very all the details.
It's very interesting, and yes, it opens some doors, very interesting doors.
Thank you.
Okay, anyone else? So I think that is no one else. So what is the role of the magnetic fields in these kind of scenarios?
Yeah, the magnetic fields enters in a similar way to what we said before, with Diego, that if you have a strong magnetic field, the jet will be more collimated, and it will be easier for the jet to break out from the supernova. That's the main role of it. The supernova can also be aspherical, because in the paper we presented different simulations of with different structure of the supernova, spherical supernova or aspherical, and depending on that also you can get a different result. Yeah, but the main role of the magnetic field is related to the collimation of the jet, and how well collimated the jet will be maintained during the propagation inside the star. So if you have a strong magnetic field, it will be in principle easier for the jet to break out.
Okay, so sorry, we have one more question from Enrique.
Hi, yes, Fabio. So, quick question. So, if you launch first the supernova comes out from basically the surface of the proton-neutron star, and it sweeps away the material that's on top of that. So, aren't you worried that if you launch first the supernova, you will sweep away all the material and you will have no accretion disk to launch a jet?
Yeah, depends on the mechanism you are considering. You mean in the case of imagine the case of a disk wind. You produce a disk, you accrete mainly from the equatorial plane, the material. You begin launching the disk wind, which will make the supernova. And but some material is also accreting from the polar region. I don't know. It will be a very messy situation. But yeah, I think it's possible. You mean that in that case they should be launched at the same time?
So I would imagine that if you form an accretion disk, you launch your jet. The jet forms a cocoon inside the star, and that cocoon can trigger the supernova. And if you have on top of that the wind from the disk, that could also help the cocoon be energized and launch a very energetic supernova, which is what you see. You even call it a hypernova. But if you go the other way around with it, at least with the typical mechanism for a supernova, which is the rebound, then you could blow away the disk. So that was, but once you include the winds and those things, it could be okay.
Yeah, the first point you made, that's not correct. No, you can't produce the supernova with the jet alone and the cocoon alone. You don't have enough energy to produce. Actually, have here. Yeah. So there was a paper. I was putting this in the presentation that I took it out because for the lack of time. So there are this paper by Shankar. There is this paper by Shankar et al. 2021, arguing that if you have just with the jet, you can get enough nickel to reproduce the supernova. That's incorrect, because just from a very qualitative.
Yeah, but you can. Well, if you take the model from Metzger and company, they can produce all the nickel in the disk.
Oh, in the disk. Oh, yeah, okay, in the disk, not in the jet. Yeah, yeah.
Yes.
Yeah, in the disk. Yeah.
So when the cocoon from inside the star, not the cocoon outside the star, when that reaches the the disk from both sides, you blow away part of that material. And
Yeah, that's interesting. So the evaporation of the disk due to the interaction with the cocoon. Yeah, you have also strong radiation from that. Yeah, that's a pretty interesting problem, no?
right.
What happens with the disk when you have the cocoon interacting with it?
Okay,
Right.
so if you want to continue this discussion, please do it in the discussion time. So let's continue with the other talk, the OHP Mistral spectral image for transients from